In the conservation laboratory of the Cairo Museum in 2019, a technician running a portable 3D laser scanner across the surface of a colossal seated figure of Ramesses II produced a dataset that nobody looking at the statue with their eyes could have predicted. The scanner works by firing millions of laser pulses at the surface and measuring the exact distance each pulse travels before bouncing back, building a point cloud so dense that it captures the three-dimensional geometry of the surface at a resolution of fractions of a millimeter. The method is used in aerospace manufacturing quality control. It is used in the production of precision optical components. And in this case, it was being used on a piece of red Aswan granite that was carved and polished somewhere between 3,200 and 3,400 years ago by workers using tools made of copper and stone and wood, without any instrument capable of measuring what they were doing to the tolerances that this scanner was now revealing they had achieved. The surface of the statue, across areas of several square centimeters measured in multiple locations on the flat planes of the torso and the seat, showed flatness variations of between 4 and 12 thousandths of a millimeter. The laser scanner was measuring the topology of the granite surface at a scale where the individual crystal grains of the rock itself, the quartz and feldspar and mica that make up Aswan granite, are visible as microtopographic features. And across the flat surfaces of the statue, averaged over areas large enough to smooth out the crystal scale texture, the surface was flat to a degree that matched the specification of a precision-machined reference flat used in a professional metrology laboratory. Not approximately, not roughly, to the tolerances that precision-machined reference flats are manufactured to achieve, on a piece of stone carved by a civilization that had been extinct for more than 2,000 years by the time the lathe was invented. This is the entry point of the problem that Grok AI was given, when researchers and users across multiple platforms began submitting the complete body of Egyptian granite working evidence to its analytical framework. Not the entry point of the controversy. The controversy has existed since Flinders Petrie first measured the interior of the King's Chamber in 1881 and found tolerances that he published carefully, without exaggeration or speculation, and that have been argued about ever since. But the entry point of the synthesis that AI is uniquely positioned to produce, a coherent account of what we know, what we don't know, and where precisely the gap between those two categories sits in the physical evidence. Because the gap is real, it is specific. It is not located where the alternative archaeology community usually claims it is, not in the bulk of Egyptian granite work, which the mainstream toolkit of copper, sand, dolerite, and flint explains thoroughly and convincingly, but in a specific, well-characterized, consistently appearing category of the finest work that the documented methods, as experimentally demonstrated by the researchers who have most rigorously tested them, do not reliably reproduce. Understanding the exact shape of that gap requires understanding the full toolkit first, including the parts of it that work exactly as mainstream Egyptology describes. Granite is a relatively simple thing at the physical level. A mixture of quartz crystals, feldspar crystals, and flake-like mica minerals, grown together under intense pressure and heat, deep in the Earth's crust, and then exposed at the surface by the erosion of the rock above them. The specific Aswan granite that the Egyptians used for their most important construction and statuary work is a pink variety. Pink from the potassium feldspar that dominates its composition, with quartz as its second most abundant mineral and biotite mica, giving it the dark flecks visible in any polished Aswan granite surface. Quartz, the hardest mineral in granite, registers at 7 on the Mohs hardness scale, the 10-point scale that measures a material's resistance to scratching. Feldspar registers at 6 to 6.5. Mica is softer still, at 2 to 3. Copper, the metal that Egyptian tools were made from in the Old and Middle Kingdom periods, registers at approximately 3 on the Mohs scale, 3 against 7. A tool that is harder than the mica in granite, but softer than both the feldspar and the quartz. Any naive understanding of material science says that copper cannot cut granite, because cutting requires the tool to be harder than the material it is cutting. And any naive understanding of material science is missing the mechanism that actually makes the system work. The quartz sand, specifically the combination of copper as a delivery mechanism and quartz sand as the actual cutting medium, the mechanism that Dennis Stocks established through systematic experimental archaeology across the 1980s and 1990s at Manchester, and that his published experiments confirm produces material removal rates and surface characteristics consistent with most of the surviving evidence from Egyptian granite working. Quartz sand, with its hardness of 7, is the abrasive. The copper saw or drill does not cut the granite. It delivers the sand to the granite surface under controlled pressure and controlled motion. The sand grains, each one a tiny hard-edged crystal, abrade the granite molecule by molecule, grain by grain, through the aggregate effect of millions of tiny contacts under consistent force. The Stocks experiments were not theoretical. They were conducted with physically reconstructed period-accurate tools on actual granite. The copper tube drill, loaded with quartz sand and rotated under consistent downward pressure, produced measurable material removal from granite surfaces. The copper flat-bladed saw, loaded with sand and moved back and forth across a granite block surface, produced measurable cutting. The results were published with specific measurements: the rate of material removal per hour of operation, the amount of copper consumed per unit of granite removed, the depth and character of the cut surface. These measurements are reproducible. The mechanism is real. The consensus around copper plus sand abrasive as the primary cutting mechanism for Egyptian granite sawing and drilling is not a default assumption or a failure of imagination. It is the result of experimental work that produced specific, quantified, published results consistent with the surviving archaeological evidence. For most Egyptian granite work, the bulk of the two, 3 million blocks in the Great Pyramid structure, the rough-cut granite for the interior passages and chambers, the shaped but not highly polished surfaces of structural elements, this mechanism, combined with dolerite pounding for quarrying and rough shaping, explains everything the archaeological record shows. The physical evidence at the quarries at Aswan is straightforward. Dolerite balls of various sizes, their impact marks visible on granite surfaces where work was interrupted, the channels pounded around the unfinished obelisk by teams working section by section across a 42-meter length. The tool marks are unambiguous. The mechanism is physically understood. There is no mystery in the bulk granite work. The mystery is in the finest 10%. Or perhaps the finest 5%. The specific category of Egyptian granite work that shows surface quality, geometric precision, and drilling characteristics that the experimental demonstrations of the copper plus sand mechanism have not reliably reproduced. And understanding what that category contains, what the specific artifacts are, what the specific measurements show, and what the specific gap between the experimental results and the surviving evidence consists of, is the contribution that a full synthesis of the evidence produces. Begin with the oldest granite work in the Egyptian record, because the chronological picture is itself revealing. The most puzzling examples of Egyptian granite working do not all come from the Pyramid Age. Some of the most technically challenging surviving granite vessels, small, hollow containers with walls thin enough to be translucent in the case of the finest alabaster examples, and almost as thin in the hardest granite and diorite pieces, predate the Old Kingdom pyramid building program by several centuries. These vessels, found in pre-dynastic and early dynastic contexts dating to approximately 3500 to 3000 BCE, were produced before the institutional infrastructure of the pyramid building state existed, before the large-scale organized craft workshops of the Old Kingdom were established, and before any of the documentary evidence of construction methods that we have for the pyramid period. Yet some of them are extraordinary. A granite bowl with walls 3 to 4 millimeters thick across a diameter of 30 centimeters requires the material to be removed from the interior in a circular controlled path that becomes progressively more difficult to sustain as the walls thin. The outside surface of the bowl and the inside surface of the bowl must be produced to consistent wall thickness. The exterior geometry must be known well enough during the interior drilling to know when to stop. In the finest examples, the rim of the vessel, the thin annular edge where the interior and exterior surfaces converge, is finished to a sharpness and regularity that requires the final stages of material removal to be controlled with exceptional precision. The pre-dynastic vessels represent the earliest challenge to the simple version of the copper plus sand narrative, not because they are impossible with that mechanism, but because producing them at the quality level of the finest examples requires either extraordinary operator skill applied consistently at the limits of what the mechanism can achieve, or some additional advantage in the process that we have not fully characterized. The existence of these vessels before the Pyramid Age also suggests that the toolkit for fine granite working was already mature, already pushed to a high level of refinement, before the Great Fourth Dynasty construction program began. The pyramid builders inherited an already developed craft tradition rather than inventing it. The second category of challenging evidence is the one most extensively discussed in the technical literature, the drilling cores, specifically the examples that show the anomalous surface characteristics that Petrie first described in 1883. The mainstream account of Egyptian tube drilling with copper and sand produces drilling cores with a characteristic surface morphology, a surface that shows a regular depth variation as the drill crosses the boundary between harder quartz crystals and softer feldspar, consistent with a loose abrasive process in which individual sand grains contact the harder mineral less effectively and erode it more slowly than the softer mineral surrounding it. This produces a microtopography on the core surface where the quartz crystals stand slightly proud of the surrounding feldspar matrix, and where the groove depth varies as the drill crosses mineral boundaries. This is what most Egyptian drill cores look like, and it is exactly what Stocks's experiments reproduce. The loose abrasive process leaves the mineral scale fingerprint predicted by the physics of differential hardness, and the Egyptian cores that show this fingerprint are consistent with the loose abrasive copper tube drill mechanism in every specific detail that can be measured. The handful of cores, the specific small category of drilling evidence that has been most studied and most debated since Petrie first described them, show a different surface. The depth of the groove is consistent across the mineral boundary. The quartz crystals are not proud of the surrounding matrix. The surface shows a regular machined quality rather than the irregular mineral-following quality of the loose abrasive process. And the specific example that has attracted the most sustained attention, the core in the Petrie Museum in London that is catalogue designated core number 7, shows a continuous spiral groove maintained through 4 complete revolutions at a consistent pitch and consistent depth that independent examiners, including engineers from Rolls-Royce Aerospace who examined it in 1999, have confirmed is genuinely spiral rather than a series of disconnected rings. Grok's synthesis of the full body of evidence around this specific category begins with an acknowledgement that is important but frequently overlooked in popular treatments of the subject. The anomalous cores represent a small fraction of the total drilling evidence from Egyptian sites. The great majority of Egyptian drill cores show exactly the surface characteristics predicted by the loose abrasive mechanism. The anomalous examples do not represent a different system from the rest of Egyptian drilling. They represent the outer edge of the distribution. The question is whether the outer edge of the distribution can be explained by the same mechanism that explains the center of the distribution, by invoking variations in the specific conditions of its application, or whether it requires an additional mechanism. The key variable that the loose abrasive mechanism has difficulty accounting for in the anomalous cores is the uniformity of groove depth across mineral boundaries. The physics argument is straightforward. If the abrasive is loose, if the sand grains are distributed randomly in the contact zone and free to concentrate where the material removal resistance is lower, then the softer minerals will be removed faster, and the groove will be deeper in the feldspar than in the quartz. If the groove depth is uniform across both minerals, the most natural explanation is that the abrasive is not loose, that it is either fixed in a matrix that holds each grain at a consistent height relative to the grinding surface, or that the contact pressure is high enough and uniform enough to drive all grains, regardless of the hardness of the mineral being contacted, to the same depth before they lose their cutting edge. The fixed abrasive hypothesis, the idea that the cutting medium was embedded in a matrix, perhaps a softer stone that held the grains at consistent heights. The way the binder in a grinding wheel holds abrasive grains in modern machining has been discussed in the technical literature. An emery stone, for example, corundum-bearing rock that is significantly harder than the feldspar and granite, but composed of a fine-grained matrix that holds the corundum grains in a consistent surface, could theoretically produce a grinding surface that contacts both quartz and feldspar at consistent pressure and consistent depth. Emery was available in the ancient world from deposits in the Aegean and from several African sources, and there is documentary evidence of emery use in the ancient Mediterranean, though direct evidence of its specific use in Egyptian granite working is limited. The high-pressure argument, that the contact pressure between the drill and the core surface was high enough to drive consistent groove depth regardless of mineral hardness, is also physically coherent. If the normal force applied by the drill is sufficiently high relative to the strength of the abrasive grain, all grains reach their limiting depth before being crushed or expelled, regardless of whether they are cutting quartz or feldspar. Achieving this consistent high-pressure contact across a rotating drill tube requires the drill to be well-centered, the downward force to be applied evenly, and the rotational speed to be controlled within a range that prevents the abrasive from either skipping across the surface, too fast, or being crushed before it has cut, too slow. These conditions are achievable with the mechanical equipment available to the ancient Egyptians, but they require a level of process control that is not automatically guaranteed by the simple copper tube and sand system as commonly described. The colossal statue surface finishing problem sits in a third category from the drilling evidence, one where the physical mechanism is different and where the specific challenge is the scale of consistent precision rather than the specific character of the surface. Producing a flat surface on a small area of granite is achievable by progressive hand lapping, the same process used to produce optical flats in glass, in which two surfaces are worked against each other with progressively finer abrasives until the contact between them is uniform. The physics of hand lapping rewards patient, skilled work, and the process converges on flat even if the operator cannot directly measure the flatness. The surfaces tell each other where the high spots are by the uneven contact, and the abrasion removes the high spots preferentially. Scaling this process to the areas of the colossal granite statues, the flat planes of the torso, the seat, the arms, while maintaining consistent flatness tolerances across areas of several square centimeters, requires either very large lapping reference standards that are themselves flat, or a finishing process that can read the local flatness condition continuously and remove material only where correction is needed. The large reference flat approach is plausible in principle. A large flat granite slab used as a reference to check the statue surface could have served this function, with the lapping process run against the reference flat rather than against an adjacent statue surface. The practical limitation is that producing the reference flat itself requires a reference, and at some point the process of producing consistently flat surfaces becomes recursive in a way that requires either an external measurement standard or a mechanism that inherently produces flat surfaces without one. The laser scan data from the 2019 Cairo Museum survey, showing surface flatness in the sub-tenth of a millimeter range across multiple locations on the Ramesses II statue, does not prove that hand lapping cannot produce this quality. It establishes that this quality was achieved, and it provides a quantitative target against which experimental replication can be measured. No experimental replication of the Egyptian granite finishing process, using period-accurate materials and methods, has been published that demonstrates the same surface quality across comparable areas. This is not evidence that the ancient process was impossible to replicate. It is evidence that the replication has not yet been done, and that the gap between what we know is achieved and what the experimental demonstrations have reproduced is real and measurable. The hardening copper debate adds a specific materials science dimension that is frequently omitted from popular discussions of Egyptian granite working. Modern pure copper is relatively soft, approximately 3 on the Mohs scale, comparable to limestone, but copper's mechanical properties are not fixed. Work hardening, the increase in hardness and strength that occurs when copper is repeatedly deformed, as by hammering or drawing, can significantly increase the hardness of copper tools beyond the annealed starting value. Archaeological metallurgists, analyzing Old Kingdom copper tools, have found microstructures consistent with work hardening in some examples, evidence that the copper was repeatedly worked after initial fabrication to increase its hardness for specific applications. Hammering a copper chisel's cutting edge, for example, can increase the hardness of the edge zone by a factor of 2 or more, reducing the rate at which the edge deforms under cutting loads. This hardened copper is still not harder than quartz. Work-hardened copper reaches approximately 4 to 5 on the Mohs scale. Harder than feldspar, but still softer than quartz. It would not change the fundamental requirement for an abrasive intermediary in the granite cutting process. What it would change is the durability of the copper tool. A harder copper edge would maintain its shape longer under the contact loads of the grinding process, allowing more consistent contact geometry and therefore more consistent abrasive contact with the stone surface. This is potentially significant for the finest work, where the consistency of the contact geometry directly affects the uniformity of the surface produced. Some researchers have additionally proposed that the Egyptians may have used bronze, the copper-tin alloy that was being developed in the ancient Near East during the Old Kingdom period, for the finest cutting applications. Bronze is significantly harder than copper, reaching 6 to 7 on the Mohs scale in compositions with higher tin content, which would give it cutting capability against feldspar without requiring a sand abrasive intermediary. The evidence for systematic bronze use in Egyptian granite working during the Old Kingdom is limited. Bronze was scarce and expensive in this period, and copper remained the dominant tool metal. But the possibility that specific fine cutting operations used bronze implements that left characteristic marks different from those of copper and sand processes has not been ruled out by the available evidence. What Grok's synthesis of the complete evidence base produces is a 3-tier picture of the Egyptian granite working toolkit and the state of explanation for each tier. The first tier, quarrying and rough shaping, is thoroughly explained. Dolerite pounding, water expansion in wooden wedges, and rough copper chiseling on fractured surfaces account for everything the quarry evidence shows at Aswan and at the construction sites. The dolerite balls are the dominant tool, and their impact marks on granite surfaces are unmistakable and reproducible in experimental conditions. No significant explanatory gap exists here. The second tier, precision sawing and tube drilling for standard construction and statuary applications, is substantially explained by the copper plus sand abrasive mechanism that Stock's experimental archaeology demonstrated. The majority of the surviving evidence from this category, most drill cores, most saw cuts, most worked granite surfaces in the archaeological record, shows the characteristics predicted by the loose abrasive process. An experimental replication has produced results consistent with the rate of material removal and the surface quality visible in these examples. Remaining questions in this tier concern the specific operational conditions, pressure, rotational speed, sand grain size, and concentration that produce the specific results documented in the archaeological record. And they are the kind of questions that more refined experimental work could address. The third tier, the finest precision work, the surface quality of the best colossal statues, the anomalous drill cores, the thin-walled pre-dynastic granite vessels, the sarcophagus surfaces that Dunn measured in the Serapeum, is where the explanatory gap is real, specific, and not yet closed. The gap is not large in the sense of being unbridgeable. The physics of abrasive grinding, even with period-accurate materials, is capable of producing the surface quality measured in the finest Egyptian granite work. Capable in principle, achievable by processes that converge on high flatness and high surface quality if applied with sufficient time, skill, and process control. The gap is large in the sense of the distance between what the documented experimental demonstrations have achieved and what the physical measurements of the finest Egyptian granite work show. That distance has not been crossed by any experimental program using period-accurate tools. Grok identifies this gap not as evidence of lost technology or external intervention. It identifies it as evidence of something more interesting and more historically significant: craft knowledge. The difference between a copper tube drill producing an irregular, mineral-following groove and a copper tube drill producing a consistent spiral groove is not a difference in tool technology. It is a difference in process knowledge, in the specific, accumulated, experientially developed understanding of exactly how to operate the tool, at what pressure, at what speed, with what abrasive grain size and concentration, under what conditions of lubrication and cooling, to achieve a specific result rather than an approximate one. This knowledge is not transmissible through a description of the tool. It is transmissible only through practice, through the acquisition of physical skill that allows the operator to read the feedback of the process in real time and adjust accordingly. A stoneworker who has spent 20 years drilling granite with copper tubes and quartz sand knows things about that process that no experimental replication trial of a few weeks can access. They know how the pitch of the sound from the drill changes when the abrasive concentration is right versus wrong. They know how the resistance under their hands changes when the grain size is producing cutting versus skating. They know when to add sand and when to wait, and when the tool has consumed its cutting edge and needs to be retired. This knowledge, embodied in the hands and ears and judgment of specialist craftspeople who spent their careers in the stone workshops of the Royal Construction Program, was the operational mechanism that bridged the gap between what the tool can do in principle and what the finest Egyptian granite work shows it achieved in practice. That knowledge is gone. The craft tradition that carried it was disrupted by the decline of the New Kingdom, the end of the large royal construction program, the transition to Greek and then Roman administrative systems, and ultimately the abandonment of the hieroglyphic tradition that had been the institutional context for transmitting specialized knowledge. What remains is the physical evidence of what the knowledge produced: the drill cores, the statue surfaces, the sarcophagus walls, the granite vessels, and the tools that carried out the process. What does not remain is the operational knowledge that closed the gap between the tool's physical capability and the work's physical quality. Grok's conclusion, when it synthesizes everything, is honest about this. It does not claim the standard toolkit fully explains everything. It does not claim that anything unexplained requires a non-standard explanation. It claims that the standard toolkit, operated by practitioners with the specific, deeply accumulated, experiential knowledge of a craft tradition maintained across centuries of intensive granite working, was sufficient to produce everything the Egyptian granite record shows, but that the specific knowledge that made it sufficient is not in the archaeological record, not in the experimental replication trials, and not in any written description that has survived the 4,000 years since the last Egyptian granite workshop was active. Scientists cannot fully explain how the finest Egyptian granite work was produced, because the knowledge that produced it was not written down. It was carried in the hands of people who are gone, and the gap between what the tools could do and what the evidence shows they achieved is the negative space left by that lost knowledge. Not a mystery requiring an extraordinary explanation, but a human story about the depth of what can be known by practice that cannot be reached by analysis. Subscribe, because the experimental archaeologists who are still trying to close that gap with period-accurate tools and modern measurement are getting closer every year.